Hello everyone. As I've already been introduced, I can go through this nice and quickly. I'm CTO at Paramus, and I've been working with OSGi for quite a while now. I'm chair of the IoT expert group, which has absolutely nothing to do with what I'm about to talk to you about, because this comes from the work I do with the enterprise expert group, because I am very interested in asynchronous and distributed systems, and obviously part of that is reactive design, which is a lot closer to what we're going to be talking about here. I also have a book which, quite frankly, has been around for a while, so if you haven't bought it yet, you're probably not going to. So I'm going to start very quickly talking a little bit about working with data. And we'll start with something that I am sure we're all familiar with, which is iterating in Java. Now, Java has collections, and they make iterating pretty easy, so I'm fairly sure we've written code like that, and probably even that. For those of you who came to Java after Java 5, you may actually be wondering what the other two are. But you know, we've probably all written that code. And the thing is, there's a problem with iterating like that. Because it's pretty easy. I mean, we saw I got 3 snippets that were really basic, but everyone immediately knew what they were. But that version is really bad if what you've got is a linked list. It will perform horribly as the list gets bigger. I mean, like really horribly. And there's no real way to know in advance, if you're just given a list, whether this is okay or not. External iteration is there, and you're confusing your code with logic that shouldn't really have to be there. If you want to parallelize this, it's really hard. You know, you can do it, but it makes your life a real mess when really what you wanted to do was just say, do this thing for every element in this collection. And that's why Java 8 introduced the updates to the Collections API to support internal iteration. So this is where you see people use lambdas, and it's where you hear people talk about the streams framework. And it's because you've got functional concepts now that allow you to make much better use of the available tools. You can write code that's easy to read, it has just your logic in it, and you're not full of all of this control flow stuff that gets in the way. So streaming with a collection is really easy. For those of you who don't get to use Java 8, I am sorry for you, because this does make life a lot easier. Because you've separated the what from the how. This just says, I want to do this thing. It doesn't say how it has to do it. That means that the list can parallel process it. If it's a list that supports parallel access, then it can fork off lots of threads if it deems that the list is big enough and do the work much more quickly for you. You also get functional pipelines, and this is where it gets really cool, because you can do a series of operations in a pipeline without having to do all of the loop, control flow, switch back, drop this thing, continue statement. All of this gets turned into just counting across the ages that were in this list. So these things are intermediate operations. You see these two here. The map and the filter, those are things that are happening in the pipeline. And we also have a terminal operation, which is count. And that's the thing that's actually giving you a result. And that's an important thing for us to remember for the rest of the talk. So, number of useful properties in a Java 8 stream. Firstly, they are lazy. And that's really important because it means the stream is only processing data on demand. And that's what the terminal operation is doing. The terminal operation is triggering, okay, now start getting the data. If you do as many intermediate operations as you like, if you never call a terminal operation, no data will ever be retrieved from that collection. And they can short circuit. So certain operations don't actually need to see the whole stream to get the answer. Good examples are find first and find any. The moment that you get an answer, who cares about the rest of it? So this is really good because you end up not having to worry about, in the loop, oh, where do I put my break statement? How do I get out of the loop early? This handles it for you because all you do is you process the minimum amount of data you need to get the answer that you want. A really important thing, though, is that the stream is pulling this data from the data structure. There's no super magic here. Underneath the covers, it's doing something that looks a lot like taking an iterator and iterating. It's more complicated than that because they've done a number of deep optimizations under the covers to make it perform really, really well. But fundamentally, you could re-implement it as pulling from an iterator. It's not more magic than that. So streams of data. And this is where stream is a bit of an overloaded concept, and it's going to be like that forever, I'm afraid. Before Java 8 came along, when people said streams, they meant I/O streams. That's what streams were. It's not what they mean now, but that's okay. The thing that we didn't really think about it is you still iterate when you've got an input stream. This piece of code where you're fairly inefficiently reading 1 byte at a time, but you're iterating over that stream. You're just getting each byte and processing it in turn. But the big problem with an input stream that doesn't happen with a Java collection is that this input stream can block. If this is data you're reading from a network, you don't know when that next byte is coming along from the other end of the network. It could be 2 seconds, it could be 10 minutes that you're waiting, and you're blocked. And that's really bad because your thread just gets stuck, and there's not really anything you can do. So you've got Neo, and yes, you've got non-blocking I/O there, but how many people use raw Neo for their day-to-day coding? Yeah, that's about what I figured. It's really, really hard to use Neo right. It's brilliant, and it's the source of some incredibly high-performance frameworks and really great tools, but trying to use it just as normal stuff where you don't want to have to be thinking, okay, let's go 10 levels deep in the design and really make it work. Neo is just too hard. So we're kind of stuck in this situation. But aside from the blocking, an input stream is an ordered collection of bytes. So it could make sense to stream over these bytes. You could have methods that allowed you to do it. So you can do for each bit of data, but the problem is this input stream might block. So whilst we've got that call, we make the call, and then we don't know how long that's going to take. If the input is asynchronously arriving, we're wasting a huge amount of resources doing this. We're just stuck waiting for the other guy who's pushing stuff over the network, and if he's slow, we're slow. That's not what we want. Then we also have the problem where a slow processing function may not process the data as fast as it's arriving. And this is why TCP has buffers, and people used to tune them quite heavily to try and make their network work as fast as it could, because line speed was a problem then. It's not so much a problem now, so mostly we don't bother tuning our TCP buffer. But fundamentally, there's a buffer there because they're worried that you're not going to read the data as fast as it comes in. And in fact, a really rapid burst of data can completely overwhelm. If you're using something like UDP, where, yes, there's a short buffer, if the buffer gets full, you're just going to start dropping stuff. You will lose data because you're not pulling it fast enough. You can even overload the network card and basically take down a machine. So effectively, a denial of service attack is what's happening here. So asynchronous makes things a bit more complicated. And this actually is true whether you're using bytes or objects. If you've got asynchronously arriving data, then you need to think about what happens when either nothing arrives for a long time or a lot arrives all in one go. Those are problems that we have that you don't normally have to deal with when you're doing pull-based work. And fundamentally, Java 8 streams can't cope with this. And the reason they can't cope with it is they were never designed to do it. It's not that they're bad, it's just that they are not asynchronous things. They are designed for working with collections where you've already got the data. So, what if we did want to make something asynchronous and push-based? So, it's a fundamentally different thing. As I'm saying, a push-based stream versus a pull-based stream, they're just not the same. You've got a processing function, and it's being called when data arrives, not when it's finished processing the previous thing. So it does give you the ability to get really high throughput and really good parallelization just implicitly. These are good things. But it means that your terminal operations have to also be asynchronous and non-blocking. You can't say, do my terminal operation and wait for the answer, because that's not asynchronous, and who knows how long it will take. So the promise is something that could help us here, because promise is the primitive of asynchronous programming. It's a value that doesn't exist yet, but will exist in the future, and you'll get told when it's there. So rather than returning values from our terminal operations, we could return a promise. So that's this result that will be resolved later. So we don't have it now, but we will have it. And OSGi has promises, so maybe those are going to be a good option. So if we were to take a Java 8 stream and try and make it push, because the Java 8 Streams API is great, I love it. You know, I may have been saying some things about using it asynchronously not working well. As a synchronous API, it's brilliant. But can we make it push-based? It turns out we actually can. So if we change the return type of all the terminal operations so that rather than returning the value, it returns a promise to the value, then we're actually most of the way there, because suddenly count is non-blocking. And eventually we'll get the count, but for now, you're just going to be able to carry on and do whatever it was that you were doing before. There are a couple of problems. So actually, how do you know when an asynchronous stream is finished? And that's a big problem, because a pull-based model can just say, there's no more data. All an asynchronous stream can say is, there's no data right now. It doesn't know if more data is coming, because it's going to be pushed to it when the data appears. You also have this thing where, so pull-based iteration, you've got a break on how fast you're going to process the data, because you're taking an element, you do all the processing you're going to do, and then you take the next element, and you do all the processing you're going to do. What you're not going to end up with is suddenly a whole load of data elements are suddenly being processed in parallel when they never were before. You know, they're not arriving all at once. They're happening one at a time. So you've got a natural break for the system is currently heavily loaded, therefore we'll just keep taking things more slowly. A push-based system doesn't have this. You can just get events arriving faster and faster, and there's nothing you can do to stop them arriving faster. So actually, a single client thread can take down a server if you're doing asynchronous network or asynchronous delivery of stuff. If it's poorly written and the server is not robust to it, you can take down a server with a single client thread. So how do we fix this? Pushing raw data to the consumer, it's simple, but it's not enough. You need an event that tells them the stream is done now. And that's actually pretty easy. But this event also needs to be able to tell us when something went wrong, because a stream might end normally, and that's useful, but it's also important to know when something went wrong and we were midstream, because otherwise you see a final event and you don't know whether that was all the data, so the fact that nothing matched my filter means return true or return false, whereas actually you might have just had a break in the middle of the stream and you haven't finished processing everything, so the answer you give might be wrong. So really you should be returning a failure and saying, I wasn't able to process the whole stream. So there's, what we're proposing is a simple wrapper which will wrap up the data or a close event or a failure, and that's the primitive thing that we're passing through the pipeline. It's something that is either data or an error or a finish. So the other thing that we find is that actually I've been talking about networking purposefully because there are a lot of things that are similar between push-based streams and network data. Because you've got asynchronous delivery, potentially different rates between the producer and the consumer. And TCP has already solved the event storm problem. TCP with event storms, you get drops in the middle where routers just say, there's too much for me right now, I'm dropping this packet. And TCP is designed to be robust to that, but with a different fallback behavior. And it also has back pressure. So the producer will keep getting faster and faster and faster, But the moment that it stops getting ACKs, it will drop back. And the reason that it does that is because it doesn't know what line speed you can get between the producer and the consumer. So it just keeps getting a little bit faster and a little bit faster until it detects that the other end is not replying and saying, yes, got it, at which point you got too fast, so throttle it back a bit. And that's how you can get a really good efficient usage of the line, but without having necessarily a direct flow. So our push streams need the ability to do this. They need the ability to feed back to the data producer whether stuff is coming in too fast or could just come in a little bit faster would be fine. And the simplest way to do this is to literally say, don't call me for a bit. To give them make sure the next event doesn't happen for at least this long. Give me some breathing room. And this is where we have an async consumer, which is a push event consumer, a consumer of push events. And it's a functional interface because functional interfaces are good. We use lambdas a lot when we're doing this kind of processing, so you want things to be functional interfaces unless there's a good reason for them not to be. And in this case, we've got our single method which accepts things. You can detect the end of the stream because you've got the event, and we've got back pressure, which is this long. If you get a positive value back from calling that, then wait at least that long before sending the next event. If it's 0, then bring it on. And if it's negative, then that's me telling you I don't need any more events. And that may sound strange, but actually if you remember what I was talking about earlier, you can have short-circuiting operators. So as the consumer of these events, I may not need to see every single event before I know what the answer is. I might be able to say, yes, this stream of events contained a temperature sensor datum that was 60 degrees C. And because I know that this is an air temperature sensor in a kitchen, things are probably on fire and I need to do something now. I don't need the rest of the events. I need to call the fire brigade. That's the kind of thing that you can do. So, given we've been talking a bit about back pressure, it's probably worth talking about some other things that you tend to need in network systems or systems where you're processing data like this. So, as we said, you can be receiving events on many threads because they're being pushed to you. You don't control when the next one comes. The next one comes when someone pushes it to you. So it may come in on lots of threads, and you may also be pretty slow at processing. So buffering, what it does is it allows a thread switch at this point. There's one of the really basic things about it. So you can free up the producer's thread. Rather than you being slow and consuming the producer's thread, you get them to pop it into a buffer, and you then process it when you're ready using a different thread. It also means that you can scale up or down the number of workers you've got. So say there are 2 threads delivering incoming events, but you're slow to process them. You may actually want to have 10 processing threads consuming those events coming in from 2 threads. So incoming data is queued up until we can process it. And then the buffer itself can return back pressure, and you can return increasing amounts of back pressure the more full your buffer is. If your buffer's almost empty, more events, I'm fine. If the buffer is filling up, then you probably want to say to the other guy, slow down, my buffer's getting full. And buffering is a built-in feature of push streams, that you can buffer at any stage in your pipeline. So I was saying, as you fill up, you give more back pressure, but what happens if your buffer does fill up? So yes, you could use an infinite buffer, at which point your buffer being full is not a problem, but you don't have infinite memory, so it's really a sticking plaster. We could block, but that's not true to the asynchronous spirit of our model, and blocking the producer thread potentially for a long time could cause a lot of other problems in the system. So a good option is actually just to close the stream. If you put in a buffer and the buffer got full, then something was clearly wrong with the system, because the buffer wasn't supposed to fill up. You sized the buffer appropriately so that it would be able to cope. If the buffer gets full, Something's clearly wrong. And that's actually called a circuit breaker. And it's called a circuit breaker because it trips if you reach a certain situation. You've got too much current flowing, and then you trip the switch and the whole thing stops. And it allows the system to recover before it gets overwhelmed. And fine, it then has to recover from, I failed, why did I fail? Maybe it'll retry, and if it repeatedly fails, it'll probably just stop working and send an email to someone to say, help, it's all gone wrong. And this is a protection for how you deal with event storms, how you make sure that one failure here doesn't turn into a cascading, catastrophic failure throughout the system. So we've talked about buffering. Another thing to talk about would be windowing. Who here knows what windowing is? Few people, but some who maybe haven't heard. So if you want to have a batch of events, you can forward them in a batch, and a batch can be determined by having either an absolute number or a time window, so a time-boxed number of events. So this is actually really similar to having a buffer. And what we do is we've had all of these things pushed in, and we've reached the point where this buffer is full. And rather than that being a problem, that's our window is full, time to pass this collection of stuff onto the next stage. So they can process all of that stuff in one go. But you may choose to do it on time instead of on size. So in this case, we're saying we got the same events were coming, but we ran to the end of our time window and we didn't get the whole batch of the events that were here. We only got the first 5, because those were the only ones that arrived in time. So that's a whole bunch of cool and interesting stuff you can do with push-based streams. But it's quite important that you can get the data in the first place. So we should probably talk about what happens in the producer. Because it's not very useful to have a stream that nobody can write to. So you've got a push event source, which is a source of asynchronous data. And that, again, is a functional interface. And you pass a consumer to your source and call open. And that creates a link between these two things, complete with a closable. So the person who started it can also inject a close event and say, it is done now. I declare that it is done. And it's important that you can do that, because if you're the guy who starts the connection, you should probably be able to stop it. It's particularly useful if your data stream is infinite. Because one of the things that we don't always think about is data streams can be infinite. There is, theoretically, no final temperature reading from a temperature sensor. Right, we've got a question at the back.
Why is the variable called event? Should it be something like consumer?
It should be called consumer. Don't worry. So you may have noticed that we had a single method, but it was being given the consumer. And how do you cope with multiple registrations? You know, you've got the one source, and lots of people are registering with it, and that can be a bit complicated. You also have to deal with this back pressure. And what if you don't really understand how to deal with back pressure? Fine, if you are if you're a temperature sensor, you can probably say, oh, well, I just won't create this event. They'll skip this temperature reading because it's not that important. But if these are events that are coming in based on user clicks on a page, or loads of something when a user is going to your website, you can't say, oh, well, slow the users down. That doesn't work. These events are just going to come as fast as they come. So how do you deal with that? Because you don't always have a choice. Writing the producer should not be difficult. One of the aims is to make sure that all of this is as easy as we can make it. So we need to provide some help. We need to make it easier to write the producer. And this is why we have a simple push event source. And it gives you built-in buffered publishing. So you've got a buffer there and a circuit breaker behavior. So you can effectively ignore back pressure when you use this. You can provide it with events. And as long as the buffer doesn't get completely exploded, it's fine. If the buffer does explode, then there's an error and things are disconnected from it and you have to recover. But in the general case, that doesn't happen. You can make sure that you've got enough capacity to consume the events as fast as they're coming in. You also have a connect promise, and this is really useful because it allows you to lazily start providing the events. Because if you've got this simple push event source, then really you don't want to have to worry about when you should start. You just want to be able to get a promise and say, when this promise resolves, let's start delivering events. So it's time to have a bit of a play. You may have realized that there's something of a train theme going on. So I took a look around for an asynchronous source of events. And given that this is IoT as well, I kind of wanted it to be something that people would recognize as being IoT. And it turns out the UK rail network actually has an open data API. And it's not just an open data API where you can query it, they actually have open data streams from the trains. And they use Stomp. For those of you who don't know, that's a simple text messaging protocol. And the events that they give you are JSON, so it's relatively easy to process them. So, I'm going to start by showing you some code. So we have here our client. Let's get you to so you can see here it's a DS component with an activate. I do some pre-processing here. This is letting me get GPS coordinate information for the various train locations that exist in the UK. And you can see here I'm creating that simple push event source. I'm then having to do a bunch of netty setup because it turns out that there aren't any good Stomp clients for Java, so I had to build my own. But I can, however, run this connect. So you can see here I'm doing a nice connect, and when I eventually do connect, my Stomp handler is going to get to do some work. So we start connecting, we authenticate, we write the authentication, and then we also receive some data. And when we get told that we're connected, what we do is we wait. So you can see here, this is that connect promise I was talking about earlier. And we wait to subscribe to the topic until someone is actually listening. And that's really kind to the data provider, because it means that they're not having to deal with the overhead of pushing us messages unless we actually need the messages to be pushed. So we've got that bit. But you can also see what happens if we get a receipt. So if we receive the message, so this is when we have to do authentication. And then here, when we've actually got a message, so this is the various states of the Stomp protocol, we've been given a real message, and all we're doing here is publishing the contents of the frame, which are a UTF-8 encoded string. So this is sending the message out to anyone who might be listening. If no one is connected, then we unsubscribe, which links us back into the connect promise again, so the next time someone is asking, we'll resubscribe. So this is all quite cool. But what's actually happening on the other side of this push event source? So you can see here, what we're doing is we're creating a push stream from it. Now, a push stream is the Java 8 stream that I was talking about, where everything's been replaced with a promise. So you've got the same intermediate operations, you've got the same terminal operations, it's just all async. So you will see that this is something that looks quite familiar for those of you who've been using Java 8 streams before. We know what we were getting in was a string, and I told you it's a JSON string, but it's been batched up. So it's actually an array of the data that we want. So the first thing we do is we pass it to a split function, which basically parses the JSON array and turns it into a series of events that are the individual things in that array. So that's a flat mapping operation. It's turning one event into lots of events. Then for each of those, we have to do some pre-processing, because it turns out, whilst they're quite nice about what data they give you, it's really hard to filter it. So we have a bunch of filtering to filter out all the message types we don't care about, because there are lots of different train messages. We then find, finally, the body of one. We use Jackson to convert it into a rich object that actually we understand. And we then have one final filter here, which is we have to look for a message where a stanox is like a unique identifier for a signal position somewhere on the rail network. We have to pick one where we actually know where it is, because I wasn't able to find a complete list of every single signal location in the UK. Apparently there's some kind of terrorism legislation that it means they don't like giving that information away. Anyway. So the final thing we can do is convert this into a whole bunch of useful data, which we then pass on to someone else. Now, the person that we're passing it on to is just a really basic servlet. This is a HTTP whiteboard servlet, and it's pretty much what you would normally expect, except it's an async servlet. So someone connects to this, and what we then do is we give them a server-sent event stream with all the events from the push stream. And because it's all async and it's all async I/O, there are no threads used from the servlet container, other than the one that sets up the initial registration of the async servlet. So the single thread that's pushing data to us from the remote end, it reaches our side, we get the network stack, we've got a thread that pushes it all the way through out to all the clients. And I've tested this up to about 600 clients running one thread. So that's how cool this async stuff is. Now, you've listened to me talking about the source code for a while, so it's time to see what it actually looks like. And this is where I wait with bated breath to see whether they've... Yep, there we go. So, if I look here, you can see we've connected to the server, and those marker points that are coming in, those are live reported train sightings as trains go past signals all across the UK. So I've deliberately filtered it down to only be the trains that are currently running late, because even in the UK, that's a lot fewer than all of the trains. And it turns out that whilst the infrastructure component can cope with huge numbers of messages, the JavaScript UI really can't. It gets quite upset if you give it, tens of thousands of these.
Bad day, huh?
Well, so it's you see what you would expect, right? So the late trains are mostly in the large population centres, so London, and then the line running down from north of London down to Brighton, which is run by our worst rail operator. And then so you see there's a load more trains running late in Birmingham, a bunch more in Liverpool and Manchester, and so all over the country, this is real live data that we're consuming. This is proper IoT. But something else we can do is see that I'm also getting some events in Germany. And that's because I'm also receiving MQTT events from the OSGi train. Now, obviously, it's not really in Essen, but I had to map the locations to something that would show up on a map of this scale. But these are live waypoints that are triggered by the OSGi train driving around. So you can see that's Leipzig and Dresden. It's been in Munich and Nuremberg. So yeah, and the cool thing about this is because it's OSGi. I've got another slide for this, which was I've got some time. So I must confess, this isn't something I was expecting to show you, because it was just going to be the network rail stuff. And this morning I did just one last test. I tested it on Friday last week, but it turns out they deactivated my account over the weekend. And because they deactivated my account, I had no train data at all. And this was bad, because I knew I was going to have a room full of people expecting to see something cool. And I had nothing. I mean, diddly squat. So, thankfully I was using OSGi. And OSGi is amazing. And so I just built a new module, because you saw I had a single service which was doing stomp connections and turning it into some messages in a push stream. So what I did was I put an MQTT client and some messages into a push stream. And it turns out you can just drop it in and it does exactly the same thing, and it plugs into the UI and you don't need to worry. So it took an hour, but an hour later I was consuming live data from the OSGi train and showing it on my UI. And I was I was pleased. This was good. I had saved the day. And then they reactivated my account 10 minutes later. So it all would have been fine anyway. But that's why you've got not only UK, but also OSGi trains in your demo today. So, I feel obligated to say that it's really important that we get feedback, because feedback helps us, meaning the presenters, but also the OSGi Alliance, to put on better conferences and better talks. It's important to know, what you thought went well, what you thought didn't go well, whether the topics were interesting. All of that information is useful, and it really does get read. I know some people think, oh, I spend time filling out all of this stuff and it just goes into a black hole and no one looks at it. And I can tell you, we definitely do, so we would appreciate it if you could fill this out. Other than that, I think thank you, and it's probably time for me to take questions.
Did you mention that the PushStream specification is in the draft?
That is true. The PushStream specification is in the R7 draft. There is also a version of it in Apache Aries that's being published into the Apache Snapshots repository, so you can actually play with that code today if you want to. I think you were first the first time.
First of all, great demo. I really enjoyed that one, like always. But I was thinking I'm a pretty heavy user of both OSGi and Java.
Yep.
And they really play nicely together. And I wonder why you chose to roll your own.
Because when I use RxJava, it makes I die a little inside. The API is so horrible. So you saw the kinds of things I was doing there, the flat mapping, the mapping, all of that, in all of those layers of processing. When I started using Java 8 streams, it just immediately was a light bulb of, this is how it should be to process stuff in a pipeline. And the stuff in RxJava I find to be not like that at all. So it's not intended to say that theirs isn't, fast and doesn't work well. It's just that I know that the fundamental thing about asynchronous systems is the stuff that goes wrong is between the brain and the keyboard. People don't get how to write asynchronous well because our world is not asynchronous. We do A, then B happens. That's the way humans have evolved to think. So trying to give them a pipeline that they can build up where they can look at it and say, okay, it's that, then it's that, then it's that, then it's that, and make it work asynchronously, but not make them have to think about every step asynchronously. Much better. So that's why. Yeah?
My question, it's related as well to the RxJava. So RxJava is implementation of Eclipse.
Yes.
How is related to PushStreams? Because this specification will be part of Java 9, at least.
So this would be part of OSGi R7, the PushStreams spec. It's not tied to the core framework, though. In the same way that OSGi promises can be used independently, PushStreams can also be used independently of the framework. So you could take them and use them in a standard Java application. And our intent is simply to try to provide a better, more usable setup for handling asynchronous streams of data, particularly because when you're dealing with a modular world, it's important to have it be built right and understandable. And if you don't set those things up well, you end up with huge amounts of implementation coupling and bleeding through, and you can't ever really be modular. You couldn't ever replace an implementation.
The specification doesn't define the operations that you can do with streams. It's just only the four interfaces for the publisher, subscriber, and so my question: do you want or do you have any plans to based on the Iterating streams specification? So this means that in OSGi world we can replace standard OSGi implementation with another one, but based on the Iterating streams.
So, given what you've said, you can see why I might find it difficult to see how you could replace the implementation, because the intermediate operations are the significant part of what people want to do. And those aren't part of the standard API, those are things that are actually in Rx or in one of the other implementations. So it's very hard to actually replace one of those. Now, what you absolutely can do, and people have done, is show interoperation between PushStreams and Rx, and even an implementation of PushStreams using Rx. And I'm relatively sure, though I haven't tried, that you could do the other way around, that you could produce an implementation of, they are both solving the same problem, and they are sufficiently similar in the places that matter that you could map one to the other. It's just about what it is that's easier to use. I mean, people are using OSGi promises in preference to the promises that already existed in, say, Guava, because the API is so much nicer. And it's about trying to make something that fits with what people are trying to do. That's all. Question at the back?
So far we have been talking about the use case where you want to process an uninterrupted stream of events, and if that's not possible, with an overload, then you rather cancel and abort and say, okay, it's not possible. But there are also use cases where you say, okay, it's okay to drop some of the data, but keep processing with dropouts.
Yes.
Is there anything of that or any plans within the push stream API?
It's already in the spec, so you've got a handler policy for each buffer stage, and you can configure what it should do when it's inserting the value. So if the buffer's full, you can tell it to block, you can tell it to throw away the thing it's just received, you can tell it to throw away the first thing, or you can write your own function which does whatever you want.
Would you use PushStreams for a low latency trading application?
You have to be very careful when people say low latency trading. So below a millisecond easily, but low latency trading to some people means measuring it in nanoseconds. And so below a millisecond, yes, this will easily do it. Below a microsecond, which some people are talking about, you pretty much have to go native and totally unbuffered and single-threaded, and it's the only way you can get the latency that low. So it's always difficult, because it's what do you mean by low latency? And the more extreme you are, the more crazy your solution has to be. This is designed to be something that is more general purpose than that. Yeah?
Is there any relationship between what you presented and a framework like Akka, which is more or less implementing the same principle regarding asynchronous message consuming?
So Akka is doing slightly different things in that Akka is about exchanging messages between effectively services asynchronously, whereas this is very much about building functional processing pipelines. So you can sort of say that you can make pipelines with Akka by assembling the Akka actors in the right order, and you kind of make them into a pipeline. I don't know if you saw the Diane, it was one of the first OSGi talks, where you had a UI where you would drop components and wire them together. So theoretically you could do something like that with Akka, but It's not, again, it's a much higher level, harder to think about set of concepts than this, which is, okay, I need to do some processing, I need to do some transformations, and then I need to forward on.
So this could be used to implement event sourcing approach to develop applications and components in a way,
Yes.
and replacing completely frameworks like Akka.
Replacing or augmenting, yes. Yeah, I think I'm probably well over at this point.